Okay, so today is April 1st, 2020. And we're going to start our talking about functions. In 2.4. Okay, so functions are... So first off, we can talk about a relationship between two quantities. So for example, if you get paid $10 an hour to do a certain job, then the relationship between number of hours, X, and Y, money earned, and you get paid $10 an hour, then Y is equal to 10x. So this is nice because if you want to know how much money you're going to get if you work a certain number of hours, all you have to do is plug in that number of hours for x. So for example, let's say you worked 40 hours. So we can say 10 times 40 is equal to 400. So you should get $400 if you work 40 hours at $10 an hour. Okay. So this is actually a function. So we will be going over what can and can't be a function in this section. Okay. So in this case, we have a dependent variable. I'm sorry. This one's the y is the dependent variable. And this one's the independent variable. Since this dependent variable depends on what value of x you put in. So if I put in one value for x, the y is going to change. If I put in another value for x, the y is going to change again. Now keep in mind, it doesn't have to be y and x. You could even switch them. It could be x. You could have had x be the money earned, and y is the number of hours paid. So that's another reason that y is in this case, y is a dependent variable because the money you earn depends on how many hours you work. Okay? Okay, so you just kind of have to specify what you want and how you're you specify which variable you want to represent the different quantities, and then it's usually understood which one's the independent variable and which one's the dependent variable. Okay, so another thing we have to talk about is a function's domain and range. A function's domain and range. Okay, so the domain of a function is so you can have the domain of a function is the set of this you can draw what's called a correspondence diagram. And So a function is going to take a set of points x. This seems really weird and complicated right now, and map them to a set y. So x and y here are not, these are like capital letters. This is a set containing a bunch of points, could be infinitely many, and this is a set containing a bunch of points, could be infinitely many. So for example, you could have this correspondence function. This, you kind of draw two little circles, and then, so if this is x and this is y, and you had, in this set, you had a, b, c, and d. A, and we had 1, 2, 3. So let's say the function takes a to 1, and it takes b to 3, c to 3, and d to 4. Then here the domain of this one is a, b, c, and d, because these are all the points that get mapped to a point in y. The range is 1, 3, and 4, because 2 is left out. It's not getting mapped to. So if instead b went to 2, then we would put a 2 in here in the range. Sorry, I'm situated here. All right. Okay, so like I said, if b would have mapped to 2, or if c would have mapped to 2, then we would add 2 in the range. Okay, but let's think about another example of a correspondence or a set or a function here. Well, a relationship. A relationship, we'll go over more of this in a second. A relationship is any relationship. You can always have a relationship between two sets of numbers, but a relationship is not always a function, but a function is always a relationship. Okay, so let's say we had this one instead. We had a, b, c, d. Okay, and then we had 1, 2, 3, and 4. 1, 2, 3, 4. So if the correspondence diagram looks like this, it's not a function, because one thing we have to be very careful about is, so you can always have, for example, in this one, this is a function. Is not. So this one is a function because you can have multiple x values can have the same y values. Okay, multiple independent variables can map to the same dependent variable. However, you can't have an independent variable map to two dependent variables. Think about that example about y equals 10x, or you're getting paid $10 an hour. So if I work C hours, do I get paid $2 or $3 or whatever? So that's why you can't have one x value mapped to two different y values. But sometimes, like, maybe there's some sort of cap on how much you can make. So if I work B hours, I get $3, and if I work C hours, I also get $3. Okay. This one turns out to be what's called a one-to-one function. So you wouldn't have two x values mapping to the same y value. Okay, but so you just have to understand the difference is that you cannot have one x value mapping to two y values, but you can have two x values mapping to one y value. Okay, so the domain of a function, so I should put the domain, this one does not have a domain or range because it's not a function. This one does have a domain, and it's every value x that gets mapped to a y. So if there was some other value in here that didn't get mapped to a number, you wouldn't include it. So a, b, c, and d are in the domain. Now the range, so actually it is everything in the x value that gets mapped. So it's always this entire thing. And each value in this x has to be assigned to some y value, otherwise it can't be counted in here. So sure. Okay. So the range is just the values in this set y that that get mapped to from x. So think about it. If you had y equals x squared, right? So your x values would go from negative infinity all the way up to positive infinity. But you would only map to the 0 or positive numbers. None of the negative numbers would get hit. So the range of y equals x squared is actually just 0 to positive infinity. But the domain is negative infinity to infinity, because you can put any x you want in there. Okay. So sometimes when we're talking about functions, we call them names, right? So sometimes you might see f of x, okay? Or, so this, careful, this does not mean f times x, this just means f depends on x. It's a function of x. So f is the most common because f stands for function, but you can have g of x, h of x, you could have, there's a special one, some trig ones are sine of x, so this is just a multiple letter name here, right? You could have logarithm of x, and the list goes on and on. So for example, if you had, if we looked at that last correspondence diagram I had somewhere, yeah, here, we can write our function, we can write it as with a function named f. So it would be like, looking at that last example, f of a was equal to 1, f of b was equal to 3, f of c equal to 3, and f of d is equal to 4. Okay, remember that was for this picture here. A, B, C, D. 1, 2, 3, 4, 1, 2. So this one went here, this one here. Right, so these two go together. Okay. All right, so let's do an example. So something more hands-on and less letters and pictures, okay? So again, a relationship, if you have functions defined by ordered pairs, so like if you had the pair x, y, like we were talking about in the last couple sections, then you can make a relationship between these two variables. You can have there's a relationship between x and y. Okay, so like I said before, every relationship is not necessarily a function, but every function is a relationship. So the problem comes when you have, remember, You can have two x values mapping to one y value, but you cannot have one x value mapping to two y values. So that's what you got to look for. So if you have one x value mapping to two y values, then your relationship is not a function. So let me write that down. If one value in the domain of the relationship maps to two or more values in the range, the relationship is not a function. Okay, so so in this example, they're going to give you a list of ordered pairs, and they want you to determine whether the relationship is a function or not. So the first one is, they call the relationship R. So this is a set of ordered pairs. So the first one is 2, the second one is 1, 3, the third ordered pair is 5, 2, and the fourth is -1, -3, and then we close the set. So we have our four x values, or our domain values, -1, 1, 5, and -1. And we've got our four y values range values. Okay, so if we want to determine whether this is a function or not, we can't see it right away. One way to look at it is if we draw a correspondence. What are they called? The correspondence diagram. So the correspondence, you can put an R up here too. So we need to draw one dot for every different value in our x. So we have a -1, we've got a +1, and we've got a 5, and then here we've already written -1 down. So we're good. There's only 3 in our range, or our domain. So domain. All right. So now this -1 maps to 2. 1 maps to 3. 5 maps to 2. So that's fine over here. We already have that. But you can have that. Remember, two different x values mapping to one y value is okay. It's the vice versa. So the last one is we have a -3 now, but it says that -1 maps to it. So that's where the no-no is this -1 maps to two different values. So the relationship R is not a function. Right. So now let's talk about let's do another example. What if we had this one here? So S is the relationship -2, 1, 0, 2, 2, 1, and -1, -3. Okay, so here's our the domain and range. So we need to list out -2, 0, 2, and -1. Those are the four dependent variables. And then the independent variables are 1, 2, I've already got 1, and -3. So -2 maps to 1, 0 maps to 2, 2 also maps to 1, and negative 1 maps to 3. Okay, so nowhere do we have any one x value mapping to two different y values, so this one is. S is a function. Okay, so that's one type of, one thing we'll be talking about. So next we're going to talk about, or we can also talk about functions defined as tables or graphs. So for example, in our first example, we can graph these 4 points here. So let's graph -2, 1, 3, 5, 2, and -1, -3 on this sheet of paper here. So if I draw, R, the graph of R. Okay, so if I draw this graph here, you get a -1, and that goes up to 2, and down to -3. So there are the 2 points. Okay, and now if I draw the other 2, we've got 5, 1, 2, 3, 4, 5, comma 2. So there's another point. And then we had 1, comma 3. Okay, so that would be the graph of our relationship, those 4 points. So what about the table? You can make a table too. So you would just draw the x and y equals r of x. Okay, so we have -1, 1, 5, and -1. So a table might look like this: 2, 3, 5, 2, and -3. So here, from the table, you can see it's not a graph here, or not a function. This relationship is not a function. And from the graph, we can see it's not a function because one x value has 2 separate y values. Okay, so that's how you would do it that's how you make a graph of a relationship and a table of a relationship. You can also, so now forgetting about that example that we did, you can have functions defined by equations. Okay, so usually we have an independent and dependent variable, and for now, if I specify otherwise, we're going to have y is always the dependent variable and x is the independent variable. So sometimes you might see t as the independent variable. You might see, you can use any letter for the two, but now let's do y and x. So usually you want to solve the equation. If you have an equation that's supposed to represent a function, you want to solve it for y. Solve for y / dependent variable. Okay, so for example, if you had y minus x squared equals 0, so that could define a function. We don't know. We'll find out ways to see if it does define a function here in a second. But solving this would be y equals x squared. And then you would say, if you wanted this to be if you wanted to name this function, you could say, could name it f of x equals x squared. Okay. Okay, so then this is really saying so y is really playing the. You could also just name this y of x equals x squared. It's really just like it's really just to remember a way that if I plug in x to x squared, or if I plug in x to y, I get x squared back. So for example, if I plug in y of 3 equals 3 squared, so it's 9. So y of 3 is an actual number, where y of x is still a variable. Because x is a variable, so then if we have y depending on x, and x is a variable, then y should also be a variable. But here we're actually just, this is called evaluating a function, where we plug in a certain number, not a variable, into our function, and then evaluate it and see what our dependent variable is. Okay, so that's some function notation, but now let's talk about determining whether an equation defines a function. Oops. So this example looks like an R. No, it doesn't. Okay. So in each equation, the directions are in each equation. Determine whether y is a function of x. Okay, so here it says determine whether each equation is a function of y is a function of x. So this means you would solve it for y. So if it were the other way around, if it read in each equation determine whether x is a function of y, you would solve it for x. So y here, the way it's written right now, y is the dependent variable and x would be the independent variable. But if you flip-flop them, which you can do, it's perfectly legal, it's just names, you know, then you still use the same technique, except you just flip the roles of x and y. Okay, but here, so the first equation is 6x squared minus 3y equals 12. Okay, so we need to solve this for y, which we've worked with equations now, so we know how to do this. So I would subtract 6x squared from both sides, and you get negative 3y equals 12 minus 6x squared. Okay, so now I want to divide by negative 3, and we get y is equal to, this is the same thing as 12 over negative 3 minus 6x squared over negative 3, which this is the same thing as negative 4 plus 2x squared. So remember, if I have the rule is I can have many x. I cannot have many x values mapped to one y value, but I can have, if I plug in, I could definitely have more than one x values mapped to a y value. So this one is a function, since if let's just say I plug in, if I plug in one x value, so what we want to look for, what we would violate, is is there one value of x that goes to two different y values? So the answer is no, and it might be more clear here in a second, because I can plug in any number here, and there's only one value of y that will spit back out. Right? So on the contrary, though, like the other way that the way you might get mixed up with, let's say I plug in 1 here for x. So 2 times 1 plus negative 4 is negative 2. So 1 comma 2 is in our is is a ordered pair that satisfies this function or this relationship. So now, what if you plug in -1? Well, -1 squared is 1, times 2 is 2, minus 4 is -2. So this should actually be -2. Sorry. Is also -2. So this is fine, though. This is just two different x values mapping to one y value. So that would be kind of looking like 1, -1 goes to 2. Right? And that's okay. It's the other way around. If we had 1 mapping to two different y values, it wouldn't work. But again, if I plug in a 1 here, the only thing it's going to spit back out is a -2. Okay? And that happens for any number x. So let's talk about another one another example that doesn't define a function. So what if we had b doesn't define y as a function of x, I should have said. So y squared minus x squared equals 4. Okay. So the problem here comes from this y squared term. So if we solve this for y, we get 4 minus x squared. Sorry, this should be 4 plus, right? I'm adding x squared to both sides. So now, remember, if I take the square root of both sides, I have to have this plus or minus. 4 plus x squared. So now we have a problem, because let's say I decide to plug in any number. Let's say I plug in 1 for x here. Then I get y of 1 is equal to plus or minus the square root of 4 plus 1 squared. So this is equal to plus or minus the square root of 5. So if I plug in 1, I get plus square root of 5 and minus square root of 5. So you have x equals 1 has 2 y values. They are negative root 5 and positive root 5. So, and that goes for every x value. If you plug in any x value in here, you're going to get 2 y values back. So this one, y is not a function of x. Okay, so right. Okay. However, it does define if you just pick the plus or minus version, right? If I would just write y equals plus square root of 4 plus x squared, then it would work, right? So if you look at this graph of these two separate functions, this one would, I'm not going to write the numbers on here, I'm going to be a little lazy, so this one would be y equals positive root x squared plus 4. And this one down here, it should be symmetrical here. Y equals negative root x squared plus 4. So these two by themselves, if you just define them like this, are functions. But if you have this plus or minus, that's not a function. Or if you define it like this, it's not a function. Okay. So this might be useful here in a second when I continue to talk about other ways to find out if an equation can define a function. Okay, but now let's go back to, I already talked about this a little bit, but let's talk about evaluating a function. So this is what example, so this next example says let g be a function defined by the equation y equals x squared minus 6x plus 8. Okay, so they want you to, so it's really, you need to write y equals g of x is equal to x squared minus 6x plus 8. And we'll see why in a second, because they ask you to A, find g of 3, B, find g of negative 2, C, find g of 1/2, D, find g of a plus 2, and C, find, whoops, not C again, A, B, C, D, E, g of x plus h. Okay, so this is just substitution. So if you define it like this, then if g of x is equal to x squared minus 6x plus 8, then g of 3, you just take this 3 and you plug it in wherever you see an x over here. So this is going to be 3 squared minus 6 times 3 plus 8. Or 9 minus 18 plus 8, or, so, negative 1. Okay, so that's A. So evaluating a function is not, it doesn't take such a long time, but it still can be confusing. Okay, so g of negative 2 is negative 2 squared. Make sure you get the negative inside make sure you're squaring the negative, right? Minus 6 times negative 2. I like to write parentheses around the values I'm substituting, just to make sure I don't forget any negatives or positives here, plus 8. So this is going to be negative 2 squared is 4, minus 6 times negative 2, so that's going to be plus 12, plus 8, so that's going to be 24. Okay, so what about C? So C is asking you to do a fraction, g of 1/2. So that's 1/2 squared minus 6 times 1/2 plus 8. So 1/2 squared is the same thing as 1 over 2 squared minus 6 over 2 plus 8. So that's equal to 1 over 4 minus 3 plus 8. So that's equal to 1 over 4 plus 5. And 5 over 1 is the same thing as 20 over 4. If you multiply top and bottom here by 4, right? This has a 1 on it. So if I do 4 times 5 over 4, you get 21/4. Okay, now, so those first three are a little bit easier because they're just asking you to plug in numbers. So this next one, though, is a little tricky. So it's asking you to do g of a plus 2. So this a is just supposed to be treated as a constant. A plus 2 is a constant if a is a constant, okay? So basically, it's the same idea. You just take a plus 2 and you plug it in wherever you see an x, okay? So g of a plus 2 is going to be a plus 2 squared. Oops, 1 second here. A plus 2 squared minus 6 times a plus 2, and then plus 8. Okay, so this one we need to FOIL out. So it's going to be a plus 2 times a plus 2 minus 6 times a minus 12 plus 8. So it's a squared plus 2a plus 2a, right? A squared, 2a plus 4. Minus 6a minus 12. Okay, so minus 12 and plus 8 is minus 4. Okay, so now we have plus 2a plus 2a, that's 4a, and then a minus 6a, so we get a squared minus 2a plus 4 and minus 4. So it actually simplifies down to a squared minus 2a. All right, so now last but not least we have g of x plus h. So instead of g of x, they want to see g of x plus h. So we just take x plus h squared minus 6 times x plus h plus 8. Okay, now we just have to simplify. So again, we're going to FOIL this out. So I'm going to skip a couple steps here. So this is equal to x squared plus 2h plus h squared minus 6x minus 6 times h plus 8. Okay, so then we can combine like terms. So we have a plus 2h here and a minus 6h here. So then we just are left with x squared minus 4h plus h squared minus 6x plus 8. Oh, I made a mistake. Okay, so when I simplified this should not just be 2h. So yeah, let me rewrite this. It's bad. Sorry. Okay, so when I FOIL this out, I made the mistake. I did it in my head too quickly. It's x squared plus 2x times h, right? Because when you FOIL it out, you have x squared, x plus h, or x times h plus x times h. So that's where the 2xh comes from, plus h squared, minus 6x minus 6h plus 8. Okay, and we don't really have any like terms because we have an x squared, an xh, which is not the same as x, right? It's definitely not the same as h squared, and 8. So there's nothing we can do to simplify that. Okay, so that's what g of x plus h is. So that's how you evaluate functions. Okay, so another cool application here is so if you have another example is if you have f of x equals x cubed minus 3x plus 4, then the graph of that function is going to look like this. It's going to go at 1. If we graph it at 1, 2, and 3. So it's kind of like way up here. So it kind of goes like this. Okay? So let's say we wanted to find the area of this rectangle right here. So the rectangle LPNM. So again, this is the function x cubed minus 3x plus 4. So remember that the area, so find the area of PLMN. Right, so it just stands, PLMN just stands for the rectangle connecting those 4 points. Okay, so how can we find that area? Because, well, the area is length times width, right? Or length times height. Okay, so the length, either one of this side or this side, the length of that side, times the height right there. Okay, so it looks like we could pretty easily find what the length is. That's just going to be 3 minus 1. So that's just 3 minus 1. But how could we find the height if they don't tell us what these y values are? Well, they told us what the function is. So if I take the function and evaluate it at 1, that's going to put me right here where p is. Okay, so if I take the function and evaluate it at 1, that's going to be the length, the height above the x-axis. So perfectly what we need. Okay, so this is going to be 2 times f of 1, which is 1 cubed minus 3 times 1 plus 4, which is 2 times 1 minus 3 plus 4, which is negative 2 plus 4, so it's the area of that rectangle is 4. Okay. All right, so that's another problem you can do once you learn how to evaluate the functions. Okay, so now if we're going to talk about finding the domain of a function. So the next example here. Also, if a function is just given to you and they don't specify a domain, then you just assume that the domain is as big as you possibly can be, as big as it can possibly be without any problems. So let me, problem sounds like a weird way of defining, like what is a problem. So let's do this example and see what I'm talking about. So in the first one, we want to find the domain. Find domain. Okay, so if I had f of x is 1 over 1 minus x squared. Well, so we need to look for a couple things. Like division, in this one, we need to look for division by 0 because that point is not going to, you can't input an x that's going to cause you to divide by 0. You also can't input an x that's going to cause you to divide or take the square root of a negative number, for example. Okay, so in this case, I don't have any square roots, so I don't have to look out for that. But what I do have is what I need to figure out what values of x cause me to divide by 0. So I need to set the denominator equal to 0 to see what values I cannot have in my domain. So now I solve for x. So let's add x squared to both sides. So it's 1 equals x squared. And then if I take the square root of both sides, I get plus or minus the square root of 1 equals x. So plus or minus 1 is x. So let's check that. If I plug in positive 1 here, I get 1 minus 1 squared, which is 0. If I plug in negative 1 here, I get 1 minus negative 1 squared, which is also 0. So that's right. So my domain of this function, you can write it in interval notation as, you could write it a couple different ways. You could say x is not equal to plus or minus 1. Okay, so that just assumes that x can be anything else from negative infinity to positive infinity except for plus or minus 1. You could also write negative infinity to negative 1 open bracket you want an or negative 1 to 1 open brackets, right, because you don't want to include negative 1, or 1 to positive infinity. Okay. All right, let's do another one. So what about the square root of x plus 1? So again, we cannot take the square root of negative numbers, but there's no division. Like in this first example, there were divisions, but this one, there was a division. So in this one, there's no division. It's just the square root that we have to look for. So whatever I put in here has to be bigger than or equal to 0. So you take whatever's inside the square root, and you say, well, x plus 1 has to be greater than or equal to 0. So if I solve this for x, subtract 1 from both sides, you get x is greater than or equal to negative 1. Okay, so that, you could say that right there, that's one definition of your domain. You could also write it as the interval, so it would be a closed bracket, negative 1 to infinity. X has to be bigger than or equal to negative 1. All right. Okay. So what about, let's talk about another one. Let's do 1 over the square root of x minus 1. Okay, so this one we have a square root, excuse me. So h of x equals 1 over the square root of x minus 1. So in this one we have a division and a square root. So, so we know that, so let's first tackle the square root issue. So we know that x minus 1, just like in the last example, has to be greater than or equal to 0. Okay, but we also can, so we also have to look at the dividing by 0 issue. And the square root of x minus 1 cannot equal 0. So in this one, we're going to solve this for 0 to see what values of x give us 0, so we know not to use them. And in this one, we're just going to solve for this inequality here. So this one is the same as the last example. It's just x has to be greater than or equal to, well, you just add, rather than, in the last example, it was x plus 1 under the square root, and this one it's minus 1. So you add 1 to both sides. So in this case, we get x has to be greater than or equal to 1. In this case, we're solving it for 0, so we see what values we cannot have. So if I put this to C, okay, so if the square root of x minus 1 is equal to 0, then if I square both sides, x minus 1 is equal to 0. So then x equals 1. So if I plug in 1, I get a 0 value. So that means x cannot be equal to 1. So I have x has to be greater than or equal to 1, and x cannot equal to 1. So if I put these two together, I get that x has to be strictly greater than 1 for this to define the domain of this h function. So I would write that as either x is greater than 1 or 1 to infinity as the domain. Okay. So notice the open bracket because I don't want to include 1. All right, so one more of these and then we can move on. So let's talk about p of x equals the square root of x squared minus x minus 6. Okay, so x squared minus x minus 6 has to be greater than or equal to 0. Okay, so remember this, we're gonna from 1.6 use the test point method. Okay, so we have to factor this. So this is two numbers that multiply to negative 6 but add up to negative 1. So it's x minus 3, x plus 2. Okay, so our zeros are x minus 3 equals 0 and x plus 2 equals 0. So this one is x is 3 and this one is x is minus 2. So that's going to, remember, break up our intervals. 0, 1, 2, 3, negative 1, negative 2, negative 3, 4. Okay. All right, so our intervals are going to be from negative infinity to 2, negative 2 to 3, and 3 to infinity. So these are the three intervals we need to test. So if I choose my test point as negative 3, then negative 3 minus 3 times negative 3 plus 2 this is a negative number times a negative number So that's going to be a positive number. So if I plug in our test point was in here. So if I plug in any point in this interval, this side of the equation is positive, which is what we want. It's got to be greater than or equal to 0. So we put a little plus over here. Now if I plug in 0 here, I get 0 minus 3 times 0 plus 2. So that's actually going to be negative number times a positive number, which is a negative number. So this one, put a little negative there. And then here we can test the value 4. So if I do 4 minus 3 times 4 plus 2, that's a positive number times a positive number, so it's positive. So this one's positive. So the intervals that work are these two, right? Because if I get a negative number on this side, a negative number is not greater than or equal to 0. Okay. So we also notice that it's greater than or equal to 0. So if I plug in negative 2 and 3, if I plug in a 3 here, I get 3 minus 3. So 0 times whatever number this is definitely greater than or equal to 0. So we include in our domain the 3 and the negative 2. So it's going to be negative infinity to 2 close bracket because you want to negative 2 close bracket because you want to include it, or 3 to positive infinity open bracket. So that's how I would write it at the domain there. Okay, all right, so that's how you find the domain of a function. Let's talk about the range, finding the range. Finding the range. Okay, so let f of x equal x squared with, so this one they give you a domain, they specify the domain. So capital X is the domain equal to the close bracket 3 to 5. Okay. So note, if they wouldn't have said this, if they didn't give you a specific domain, you would just assume that x would be all real numbers because there's no divisions here and there's no square roots. So there's no problems. Okay, but now we're just going to go from 3 to 5. So they ask, the first question they ask is 10 in the range of f? So that just means we set the left-hand side of this equation equal to 10. So 10 equals x squared, and we solve it. So so that would involve taking the square root of both sides. So plus or minus square root of 10 is equal to x. Okay, so it turns out that this positive square root of 10 is, if you put that in your calculator, it's somewhere in between 5 and 3. I think it's like it's got to be a little bit greater than 3 because the square root of 9 is 3. But it can't be, it can definitely not be, it's got to be less than 5 because the square root of 25 is 5. So the square root of 10 has to be in between, somewhere in between 3 and 5. But negative square root of 10 is outside the interval, but positive square root of 10 is in there. So if I plugged in, that means if I plug in square root of 10 for x, I get 10 back. So 10 is in the range. Okay, so the next question is 4 in the range of f. Okay. So now, again, we set 4 equal to the left-hand side, or put it in for f of x, and solve for x. So plus or minus the square root of 4 is equal to x. So that's plus or minus 2 equal to x. So the problem here is if I take a look at x equal positive 2, that's not in close bracket 3 to 5. It's not in between 3 and 5. And certainly x equals negative 2 is not in 3 to 5. So so 2 is not, so this e, script e thing means in, so a line through it means not in 3 to 5. And negative 2 is not in 3 to 5. So no, 4 is not in the range. All right, so last but not least, they ask you, what is the range? So this one you can figure out if you set y equal to x squared just to figure out what the range is and then solve for x, this would be plus or minus the square root of y is x. But I know that I can eliminate the negative case because I definitely know that there are no negative numbers in between 3 and 5. So I'm going to consider square root of y is equal to x. Okay, so we're kind of taking advantage that this x squared function on our domain from 3 to 5 is increasing, right? If I take a positive number and square it, then if I have one number that's smaller than another number, and I square both of them, then the smaller number squared is going to be less than the bigger number squared. So it's an increasing function when you have positive numbers. So we're kind of taking advantage of that fact a little bit. But you can see that if I put a 3 in for x, then let's see. So you kind of want to actually look at this here. So let me see. What's a good way to define this? So if I put 3 in for x, y is equal to 9. And if I put 5 for x, y is equal to 25. So the range turns out to be 9 to 25, included because 3 and 5 are included. So again, we're kind of taking advantage of the fact that we have like an increasing function. Okay. Alrighty, so let's move on. Okay, so this next example is using the graph of a function to find the range. Okay, so that is done by looking at the graph. So I have to show you the figures here somehow. So if we're going to look at these, hopefully you can, maybe if I go down, give me a second to figure this one out. Okay, so I'm looking at these 4 graphs here. 1, 2, 3, 4. And actually right above here, we talked about the vertical line test. So the vertical line test, and we might remember that example we did the plus or minus square root example. I think it was the second example we did, where if you have a function and you can draw a vertical line, a vertical line that passes through 2 spots, then it's not a function. So this one, right here is not a function because we can draw a vertical line right here between those two dots. So it's not a function. Horizontal lines are okay. That's fine. You can have, right, you can have one y value can hit as many x values as you want, but this one says that this x value right here has two different y values. Okay, so here I can also draw a horizontal line that gets not only two, but it gets all three of them. So these two are not functions because of the vertical line test. This one, though, there's no horizontal line that connects 2 points, and same with this one. So your answer to determine which of these four are functions, this one and this one are not functions, and these two are because of the vertical line test. Okay. All right, so that's how you can use the vertical line test to determine if your given relationship is a function or not. So I would like to talk about one or two more things here before we wrap it up. So finding the domain and range of a function from a graph. So let's say we had the following graph here. So find domain and range. Okay, so we've got this function here. So 1, -1, 2, 2, 3, 4. Okay, so we've got the point here. That's -2, 1. And it's an open circle, and then we go up to here, down to 2, 2, and then back up to 3, 3. So our function kind of looks like this. I connect the dots nicely. Okay, so they want you to find the domain and range of this function here. So let's start with the domain. So the domain here is we're again looking for, so this one's 2. Let me finish labeling here. 2, 2, 1, 4, and 3, 3. So remember, we have 4 ordered pairs here that we know, and then we actually have infinitely many points that we could draw. You know, I could label this point -1, looks like 3. I could label -0.0001, and it looks like it's almost 3.5. There's infinitely many points on this graph, but they've given us 4 specific points. So these are remember, these are ordered pairs of points that we have. Okay, so more specifically, we've got a domain. You've got to look for the x values and the y values. So our x values here, our smallest x value, the furthest left we go is -2. Okay, but it's got an open circle. That'll come into play here in a second. Remember, the open circle means you do not include that point -2, 1, but you include every single point up until it. Okay, so then here, notice that we've got our graph stops here with a closed point at 3, 3. 3 is our largest x value, -2 is our smallest x value. So our domain goes, and everything in between is connected. Okay, everything in between -2 and 3 is connected. So the domain is, we say open bracket -2 because we have an open point here, an open circle. So we do not include that point, but we want to include everything up to it. And then we want to go include everything up to 3 included, because we have a closed circle there. Okay, so that's the domain. So similarly, the range, the domain was found looking at the x values. So now the range we want to figure out by looking at that should be more over there, at the y values. So we notice that our largest y value is a 4, and the 4 is a drawn in circle. So, and we also notice that our smallest y value is again over at this point 1, but it's not included. So we want to go include everything up to 1, and include everything up to 4, including 4. So let me make something clear here. So the difference between this interval here and a point is precisely that. This is an interval. So this is saying you include, this tells you, this means all the numbers in between -2 and 3, and not including -2, but including 3. This right here, all 4 of these points just give you coordinate points. Like this one's just saying this is the point x equals 3, y equals 3. So these, you have to understand the difference between a ordered pair and a interval. Okay, so let's do one more example here. So let's say we had to find same directions, finding the domain and range of this graph now. So we need to go to 1, 2, 3, 4, -3, 1, 2, 3, 4, 5. Okay, and we're going to go up to 1, 2, 3, 4, and we're going to go down to -3, -1, -2, -3, 1, 2, 3, 4. Alrighty, so now we're going to go from the graph that they give you is -3, 1, so -3, 1, and you go to -1, and it's a straight line connecting these two, and these are both shaded in. Okay, and then there's a gap, so there's a gap from 1 to 3, and then it's just this horizontal line that goes on forever. Okay, so we got to find in the gap here, and this point starts at 3, 4, and this one is 1, 1. So, okay, one last point. So on a coordinate point, you're never going to have closed brackets. The close and open bracket on a point doesn't make any sense. But on an interval, it makes a whole lot of sense. Okay, so the domain, remember we want to look for the smallest points of x and then the largest ones. But here we have to account for this gap. Like in the last one, we didn't have a gap. We had a continuous function. But here we have this gap. So we go from -3 all the way to 1 on our x values. That's the smallest and biggest on this line. And we include both the points because they're drawn in. So we can have any value from -3 including -3 to 1 including 1. But if we go past 1, if we're in between 1 and 2, we can't have that. And if we're past -3, we cannot have that. So that's one part of our domain. And now we say or, because we need to include all this stuff too. So we can include 3 and go all the way to infinity, because this arrow means it goes on forever. Okay, so the range here, now we're going to look at the y values. So we want to include, oh, this should be a -1, I'm sorry. The y value there is -1. We want to go from -1 included all the way up to 1, right? But if we go lower than -1, there's no x values that map to that, so they're not in the range. If we go in between 1 and 4, yeah, this should be moved up a little bit, sorry. It's 3, 4, not 3, 3. So it should be up here. So that doesn't affect our domain, right? Because the x value stays the same, but the y value. So we want to go from -1 to 1, or the point. So how do I talk about the single point 4? So that's actually just, you can write the curly bracket if you just want to talk about a single point. If you wanted to do like 4 and 6, you would do curly bracket 4, 6. Okay? Because if I look in between, if I look at, for example, y equals 3, there's no x value that goes to 3 ever on this graph, or 5. There's no x value, or as close as you get to 4, but not reaching 4, it's same thing. Okay, so that's why the range is just -1 to 1 or the point 4 itself, because it's just this horizontal line, y equals 4. Okay, that's about... well, actually, there's one more thing I want to talk about. Okay, so examining, this is called examining the graph of a function. Okay, so f of x is x squared minus 2x minus 3. Okay. So let's first, the first question is A. Is the point 1, -3 on the graph of x? Graph of f, I'm sorry. It's a weird looking question mark. But anyway, this is actually one that you don't need a graph of the function to look at, even though it's worded like you do. So you just take your function and you take this y value and you put it on the left side, so -3, and then you want to see if that's actually equal to if I take 1 and put it in the right hand side. So 1 squared minus 2 times 1 minus 3. So does 1 squared minus 2 times 1 minus 3 equal -3? That's what we want to see. So -3, 1 minus 2 minus 3. So 1 minus 2 is -1 minus 3 is -4. So -3, does -3 equal -4? No. So 1 comma -3 is not on the graph f. Okay. So the next question is find all values of x so that x comma 5 is on the graph f. Okay, so this one you actually don't need the graph as well. So what you do is you take your function here, and it says it wants to know all the x values where the left-hand side is equal to 5. So we take the left-hand side and set it equal to 5, and we have x squared minus 2x minus 3. And now we just take this equation and solve it for x like we've been doing, or like we've done already in the last section. Okay? So with a quadratic equation, you want to get a 0 on one side, so I'm going to subtract 5 from both sides. So this is now x squared minus 2x minus 8. So we need to factor this. So 0 equals x. So we need two numbers that multiply to -8 but add up to -2. So we have 1 and 8. That won't work. How about 2 and 4? So if I do -4 and plus 2, that would work. So x is equal to -4, and I'm sorry, x is equal to, if you solve these, right, I'm skipping a step here, shouldn't do that. So we have x minus 4 equals 0, or x plus 2 equals 0. So this is x equals 4, and this is x equals minus 2. All right, so those are the only two values of x, so that x comma 5 is on the graph f. Okay, you don't need a graph to do that either. Okay, and these last two we actually learned how to do last section. It's find, so C and D, find x and y intercepts. Okay, so let's do the y-intercepts. So the y-intercepts is when x equals 0. So if we look at our function again, our function was x squared minus 2x minus 3. So I need to plug in y, 0 for x. So 0 squared minus 2 times 0, and then minus 3. So the y-intercept is minus 3. Okay, so D, the x-intercept. So x-intercept is when y equals 0. Alrighty. So now if I have 0 equal to x squared minus 2x minus 3, I just need to solve. So this is actually x-intercepts because they're multiple. So I need two numbers that multiply to negative 3 but add up to negative 2. Okay, so that one's actually going to be x minus 3, x plus 1. Right, so equals 0. If I factor that, then so it's x minus 3 equals 0 or x plus 1 equals 0. So this one is x equals positive 3 or x equals minus 1. So those are your two x-intercepts. So now with all this information, it's actually pretty easy to draw this graph. So first off, let's start with the y-intercept. So the y-intercept, or let's do the x-intercepts first. So I know that when y equals 0, I have x equals negative 1 comma 0. That's an x-intercept. And 1, 2, 3, here's the other x-intercept. Okay, in part B, we figured out all the points where y equals 5. So here's 5. And we figured out that 4, the point 4 comma 5 is on the graph, and the point negative 2 comma 5 is on the graph. Okay, and then we also figured out that the y-intercept is negative 3. Oops, I wrote that incorrectly. So it should be 0 comma negative 3. Okay, so it's actually a parabola that looks like that. Okay, so if you find those useful things, those specific points, it's actually a little bit easier to graph it. Okay, I'm out of time, so that'll be it for today.